Okay, good morning, class. So today we're looking at probability. Homework you had exercise 7.1, 17.1. Okay, let's look at this quickly. Okay, relax, you don't mind. Yeah. 17.1 is on page. So we are on lesson 2. This is for exercise 17.1. Okay. Okay, so in 17.1 we are told number 1, roll a dice. Wait that. Okay. List all the possible outcomes. So if we list the possible outcomes here, it will simply be 1, 2, 3, 4, 5, 6. So I've listed. B. List the favorable outcomes for an event getting a prime number. 2, 3, and 5. C. List the probability of getting a prime number. It shouldn't be list, it should be calculate the probability. The probability will be the number of favorable outcomes over the number of possible outcomes. So favorable is 3 out of, which is, we all agree with that. It's fairly simple. Right? Let's go with number 3. Four cards from the suit of spades are taken out of the pack. One of these cards are chosen at random and a coin is flipped. Represent the possible outcomes for this event in a table. So 4 cards are taken. So let's assume the 4 cards are Jack, Queen, King, Ace. It could be any 4 cards. Not so, but let's go with those cards. So if we represent this in the table, and it's of spades. So here we'll have the card. We'll go across the cards. So let's go Jack, Queen, King, and Ace. As I said, it could be any of the 4 cards, of the 13, 4 of the 13 cards. And the coin is tossed. The coin can either be heads or tails. So it can be heads or Jack, heads or Queen, heads or King, heads or Ace. Jack or tails, Queen of tails, King of tails, and tails of tails and Ace. Okay, you all agree with that? So there we have represented the outcomes for the event in the table. B. What is the number of possible outcomes? It says 1, 2, 3, 4, 5, 6, 7, 8 outcomes. You guys understand? List the favorable outcomes for getting a heads and a card. So if it says and a card, that means to say it can be any card. Not so?
Yes, sir.
So how many heads are there? 4. So the probability is going to be 4 out of 8, which is? Oh. Let's look at D. D1. Calculate the probability. Okay, C says list the favorable outcomes of getting a hits. I made a mistake here. This is actually calculating probability. So list the favorable outcomes of getting a hits. So it can be a it's jack, it's queen, it's king, it's ace. Not so. Now D1, getting a card that is a hit, the probability of a card that's hits is going to be 4 out of 8, which is off. That is the calculation we just did in the previous question. D2, flipping a tails and drawing a queen. So flipping a tails and drawing a queen. So it's a tails and queen. So how many are there? 1. So it will simply be 1 out of 8. Probability of a queen and a tails will be 1 out of 8. The third question in D, flipping a heads and drawing a king or jack in a single draw. Okay? Let's say heads. Okay? Can be a king or a jack. So how many are there? Okay, in a single draw. So it's 2 out of. Probability is going to be 2 out of 8, which is 1 out of. Okay, you guys understand? Is there any confusion? Right. Question 5. A picture card from the suit of spades are taken out of a pack. This is separated. No. A picture card from the suit of spades are taken out of a pack. So how many picture cards are there? 4. What are the picture cards? Ace, king, queen, jack. Okay. Suit of spades. Whoops, that's not the spade. Okay. A card is drawn at random from the pack and a coin is flipped. Draw a tree diagram to represent the event of flipping a coin and drawing a picture card. Okay? So if I look at this here, if I flip the coin first, what are my outcomes? If I'd gone with drawing the card first, what's my outcomes? Ace, jack, queen, king, ace. One of those 4. Not so. So I'm going to go with the coin first. So it's going to be heads or tails. What are the probability on these branches? Of, you all agree with that? Then, drawing a card. How many cards are there? 4. So I'll have 4 branches, of course. Can either be ace, king, queen, jack, or set. Okay? Ace, king, queen, jack. Okay. What is the probability on this branch here? Quarter. 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 Yeah? Quarter. Quarter. Quarter and a quarter. What are my outcomes? It's ace, it's king, it's queen, it's jack. Tails ace, tails king, tails queen, tails jack. Alright. TJ is Miss Jackson. Yeah. Okay. So there's A sorted. B says use your tree diagram to calculate to find the probability of getting a tails to get a tail and a king, queen, or jack. So in other words, if you look at what they're looking for, they're saying must get the tails, so you can only go down this branch. Not so. Then it can be get a king, so is that one? Queen, which is that one? Or jack, which is that one? So it's only those three I'm going to consider. You guys understand? So let's look at the calculation now. So this should simply be B is equal to probability would be 3/8. Why? Because that's 1, 2, 3 options out of 18 total. That's one way of looking at it. Otherwise, if you had gone the other route, you could have said the probability of tails and king plus the probability of tails and queen plus the probability of tails and jack, which is 1 out of 2 times 1 out of 4 plus. So that is that path, no? Then you're going to get 1 out of 2 times 1 out of 4, which is this path here. Okay, plus 1 out of 2 times 1 out of 4. Now there are 3. 1 out of 2 times 1 out of 4. There's 3 of those. So you just say half times a quarter times, we give you 3/8. And of course, it's easy to see that this is 3/8. Not so. Now, when would we apply this method that I'm doing here is when the branches are not evenly spread. Okay, if the probabilities are not even. Let's say for argument's sake, that was 3/4 and this was a quarter. Then this method that we did in number 1 cannot apply. Why? Because of the probabilities of each will be weighted differently. Okay? But for now, it's weighted the same. So, it's fine in this example. Okay? You guys understand? Let's go to the next question. Question 6. So, exercise 17.1. There are 6 red marbles and 4 blue marbles in a bag. So 6 red and 4 blue. Draw a tree diagram to illustrate the probability of all the outcomes if. So in a single red marble is taken from the bag, then replaced. The bag is shaken before the other marble is taken from the bag. Its color is loaded. Okay. So let's look at this here. Let's say we have 6 red marbles. Okay. So you got 6. 1, 2, 3, 4, 5, 6. And 4 blue. 1, 2, 3, 4. Okay. So if I draw a tree diagram, what are my outcomes in the first draw? What are the options in if I put my hand in the bag and pull a marble out? Will be red or okay. Now, if the marble is red, what's the probability of it being a red marble? How many red are there? 6 out of 10 marbles are red. That's all. Then how many blue marbles are there? 4 out of 10. Okay. So say for argument's sake, I draw a red marble. What happens after I draw it? Replace. I put it back. So once I put a marble back into the bag, Does it change that probability at all? No, the calculation will be the same again. Why? Because it's the same amount of marbles that I started off with. Guys understand? Okay. So if I do the second row, what's my options? Red or blue? What are my probability for red? 6 out of 10. Probability for blue? 4 out of 10. Okay. If I draw blue on the first row, what's the probability? So we got again options of red or blue. What's the probability again for red? 6 out of 10. Yeah, you guys understand? So let's then calculate. This was not asked. I think this is question 7. I think question 7. In the two cases describe the previous question. Is it more likely or less likely to draw 2 red marbles? Okay, so let's work out the probability for 2 red marbles in this case. Okay? So if I work out the probability of 2 red marbles, what will happen? The branch I will follow, the path I will follow, goes around 6 over 10 times 6 over 10. Not so? So let's do that calculation. It will be 6 out of 10 times 6 out of 10. 36 out of 100, which is 9 over 25. No? Nine out of 25. Okay. You all okay with that? Now let's look at the B part. The B says a single marble is taken from the bag but is not replaced. So that scenario is a bit different. Not so. If they are not replaced, and I now draw the tree diagram, so let's pull this down here. Okay. So let's look at B. So on my first draw, what are my outcomes? Red. Could be either red or blue. Okay. What's the probability on the red branch? 6 out of 10. Blue? 4. Okay. You all okay with it? Now, say for argument's sake, the first draw, I drew a red marble. So what happens now is I got a red marble, it's not replaced. Again, my outcomes are either red or blue. Okay. But how many red marbles do I have now? 5 out of 9. Can you see that marble is gone now? So we've got 9 marbles in total. So it will be 5 over 9 and 4 over 9. Who's confused now? Yes, Michael, what are you confused about? I'm saying, why is this one crossed? He's asking. Is if I draw in my first draw a red marble. So this is what is in the bag. This is the bag. So if I throw a red out of the bag, then how many marbles are left in the bag? 9. You understand? So when they say the marble is not replaced, that means to say it's not put back in the bag, before the next marble is drawn. You understand? So there's now 9 marbles and there's only 5 red. You understand? All right. What if the first marble you draw was blue? So that one is now out. So what are my outcomes? Red or blue? So how many reds do I have? 6 out of 9 reds. Can you see them? There's 1, 2, 3, 4, 5, 6. 6, 7, 8, 9. You see that? What is the probability on your blue? 3 out of 9. Can you see that? What are my outcomes? Red, 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 blue, blue, red, blue, blue. Can I now say, if I say red, red, what's the probability of 2 reds? Can I say it's 1 out of 4 now? No. Why? Because the branches are not evenly weighted. The probability of the branches are not even. You guys understand? Right. In our previous calculation, we also calculated the probability of drawing 2 reds. Not so? So let's work out the probability of 2 reds here. The probability of red. So when I work out the probability of red, I then follow this path here. Can you see that, people? Yes. So we go. The probability of red is going to give you 6 out of 10 times 5 over 9. So we go 6 out of 10 times 5 out of 9 gives you 30. Or 0.333 or 3 recurrent. Okay, this one here was 9 over 25, which is 36. So that is basically 0.36. So which probability is higher? The first one, if the ball is being replaced. Okay, can you see that? Why? Because if the ball is being replaced, the chance of you drawing a red ball is higher. If I had gone with red-blue, you will see that the chance of you drawing a blue ball if the ball is not replaced is then higher. Okay, by going that route. Why? Because the chances of you then drawing a blue ball is a bit better if there's one red out. Okay, that explains basically question 7. Okay. Then we went on to 17.2. I explained this examples as well. Okay, settle down please if you don't mind. Here we are told that in 17.2 an ordinary dice is thrown and the number or the numbers on the upper face when it comes to rest are recorded. The faces are numbered 1 to 6. Describe the experiment or the trial involved. So basically what happens? You roll a dice or die, and if it lands on face up of 4, I record 4. Okay, once. And maybe you line on the 6. This is actually the other way around. So if I'm going to go that way, then I'm going to fit. 5, 3, 2, 1. Okay. If it lands on the 6, if it lands again on the 6, then it lands on a 4, it lands on a 1, it lands on a 4, it lands on a 6, it lands on a 3, it lands on a 2, it lands on a 4, it lands on a 4 again, and so on. Okay. To describe the experiment or trial involved, we just record the outcome. What are they looking for? This is 17.2. Yes? They say throwing a fair dice. Okay, but in our previous lesson we spoke about the dice being fair and all of those things. You guys remember? Okay, so they say throwing a fair dice. Give an example of the outcome in this case, of an outcome. It can be any one of those. You can just say one or three, whatever. Can it be seven? Why not? No seven on the dice. Okay. So you can just say any one of those six numbers. List the sample space in this experiment. So the sample space would be 1, 2, 3, 4, 5, and 6. Represent the sample space using a Venn diagram. Sample space is 1, 2, 3, 4, 5. Do you guys understand? Right. Let's look at 17.2, number 3. An unbiased four-sided spinner labeled 1, 2, 3, and 4. People, if it says unbiased, again it is fair. Okay, it's a fair spinner. That means to say it's equally likely to land on any one of those four outcomes, okay, or value numbers. Respectively spun. Describe a trial using such a spinner. So, according to them, it's a spin the spin. I don't know why they asked such a question. Spin the spin. Okay. B. List the possible outcomes. What are the possible outcomes here? 1, 2, 3, 4. Let's say sample space S for this experiment. So S is equal to 1, 2, 3, and 4. Not some. Drawing Venn diagram to represent S. 1, 2, 3, 4. Do you guys understand? Sorry? Yes? The same. 1, 2, 3, 4. 1, 2, 3, 4. 1, 4, 3, 2. Also. Order doesn't matter. Right. People, number 5. In a hat, there are 10 cards, numbered 1 to 10. One card is drawn from the hat. List the sample space. What will the sample space be here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Using the Venn diagram, sample space is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Do you guys understand? Okay, let's carry on. Events? Was that the last? Okay, so let's read here quickly. This is now for exercise 17.3. On page 3, 382. Okay, but this example is on page 3. Okay. So now we need to look at events. Okay. Reading from page 382. An event is a set that consists of what? Okay, so basically, an event is some like, if you look at inside the sample space, these are elements inside. Okay? Now say for argument's sake, we're only going to consider the multiples of 5. So 5 and 10. So that is basically a subset inside the sample space. Can you see that, people? If you say you are looking at numbers greater than 7, what numbers are greater than 7? 8, 9, 10. So that is another set inside that set. Can you see that, people? And those sets are called events. Okay. Otherwise, each one of this is called an element. Okay. And these are subsets inside. Okay. So let's see what explanation they give. Maybe you'll understand it better. Events. An event is a set that consists of one or more elements of the sample space. Okay, that's exactly what it's said now. No? So read it again. An event is a set that consists of one or more elements of the sample space. Now you're going to get some sets that overlaps, like we had here. Can you see it? Yes, this is called an intersection. Can you see that? With two subsets overlap is called an intersection. Okay? So that 10 belongs to the sample space, the 10 belongs to this set here, and the 10 belongs to that set here. Can you see that, people? We'll get down more words for this here. The diagram shows a bag with 3 blue and 5 white counters. Okay, the blue counters are labeled B1, B2, B3, while the white counters are labeled 1, 2, 3, 4, 5. Suppose a trowel consists of giving a bag a good shape, draw a counter, and then replacing. The sample space will simply be B1, B2, B3, W1, W2, W3, W4, W5. You guys understand? Okay. The number of possible outcomes in the sample space is denoted as N and S inside them. Where the N represents the number, lowercase n is the number, the count basically. Right, you guys understand? So the number S means what? The S, the sample space, okay? So yeah, how many is in the sample? 1, 2, 3, 4, 5, 6, 7, 8. Hence, here, the number on the sample space is 8. You guys understand? So let's go here quickly. Let's see if you understand what we are saying. So what's the number of the sample space here? 10. If this is A, if that is subset A, and this is subset B, what's the number in A? 2. What is the number in B? 3. What is the number in A and B? That means to say it is where it overlaps. Okay, it must be in set A and it must be in set B. What would that be? How many is in A and B? 1. It's only 10 that is in A and B. Can you see that? Okay. There is something else that's also highlighted at this point that I want to confuse you now. Okay. So let's carry on here. So here, an event drawing a blue counter, no matter its label is, or can be represented by set B is equal to B1, B2, B3. The number of outcomes in B is 3. Can you see that, people? Another possible event is W, with W1, 2, 3, 4, and 5, throwing a white counter. How many white counters are there? 5. Can you see that, people? So N of W is 5. The number in W, in other words. Okay. Note, remember, for an event to occur, it is not possible, not necessary for all the outcomes of the event to occur. If any one of the outcomes is a result of a trial, the event is said to have occurred. Thus, B occurs in any blue counter, if any blue counter is drawn. It is not necessary to draw all 3 counters before you can say B has occurred. Okay, so if you say drawing a blue counter, it can be any one of those 5 counters. Okay, Oh, sorry, 3. If it says, what's that color? White. And how many whites are there? 5. We draw any one of that 5, and then that event has occurred. Okay. It doesn't have to be white 1 or white 3, whatever. Okay. That's basically what they're saying there. Now, if two sets have no elements in common, they are called disjoint. Okay. So just go back here. Is this disjoint? Is A and B disjoint or joint? Joint. Can you see that? So let's say you got the numbers for C that is less than 5. C is less than 5, but more than 2, more than and equal to 2. Which numbers can we consider here? 2, 3. Can I consider 4? Can I consider 5? No, so I didn't put equal 5. Can you see that? So let's draw a set around C. So it's 2, 3, 4. So that is subset C. What did we call it earlier on? No, not disjoint. Elements. No, that is your element. We call the events. So this is event C. Can you see that, people? That's event C. So what is the number of C? 3. Are event C and A disjoint or joint? Disjoint. Okay, can you see that, people? This is disjoint. Another word for disjoint is mutually exclusive. Yeah, it's exclusive like. You don't want anything to do with it. It's exclusive. Okay. So set C and B are mutually exclusive or disjoint, and set A and C is also disjoint or mutually exclusive. So what can we say about set B and A? They are joined. They are joined by 10. No? And it's also, another word there, mutually inclusive. Okay. They'll probably make a note later. Okay. Or we can say they are joined or intersecting. Okay. And you'll see once we do calculations, it's not so difficult. Let's look here now. The events drawing a blue counter is, no matter what the label is, can be represented by set. I think I recopied this here. No? Yes. So I did that twice. Here we go. Venn diagram illustrates. The Venn diagram illustrates how the event W and B related to each other. There are no elements in common. Can you see there? There's no counter that plays for both teams, no? Right. You guys culture, you a bit different, must no? So I'm not gonna say it here on the record, but if you are blue, you are blue. If you're white, you're white. You're not blue and white at the same time. No? That's what I'm talking about. Right. You're not talking about the counters. Come on. Don't want to hear principal call me unnecessary. Well, I just want to do maths. No, that nobody's feelings here, no? No. Okay. Never my intention. All right. Intersection and union of sets. Intersection and union of sets. So in a hat, there are cards numbered 1 to 10. Sample, which is S, is equal to 1, 2, 3, 4, 5, 6, 7, 8. We listed this already. Not so. Consider events drawing a factor of 6. What are factors of 6? Numbers that can be divided into 6 without a remainder. Not so. Factors of 6. Right. So drawing a factor of 6 is 1, 2, 3, and 6. These numbers can divide into 6 with no remainder. Okay. Now, say for argument's sake, 6 wasn't part of the sample space. Would I have written 6 here? No. Because the numbers we choose from is from the sample space. Can't be outside the sample space. Okay. So consider the events, drawing a factor of 6, and the factors of 9 is 1, 3, and 9. So you got your event mark X and mark 1. The union or U of the two sets in all the elements of X and Y, or in Y, with both is 2, 6, 1, 3, and 9. So what does that mean? It's all the values. So if you're looking at X union Y, okay, later on you're going to see me use union or. Make a note there. Yeah? If it says X union Y or X or Y, if we look at X or Y, it's simply going to be 1, 2, 3, 6. Have to be considered 1, 2, 3, 6. Did I consider 1 already? Yes, so I don't write it down again. Did I consider 3 already? Yes. Did you consider 9? No. So there's the union. So it's all the values of set X and of set Y. Can you see that, people? Right. Now we get the intersection. Oh, no, they're not talking about that. Right. Now they ask you the number in X and Y. So how many? The number in X union Y is going to be 1, 2, 3, 4, 5. So what is the number in X? 4. What is the number in Y? 3. What's 4 plus 3? 7. But 7 is not the same as 5. Can you see that? So what I did was, the numbers that are common in both is not considered as part of the union. You don't count it twice. You guys understand? Make sense? Right. Some, huh? Right. Not completely yet. Yes, until we do examples. Okay, and I think let's get at the right time. Right. I'll see you guys after break and we will then continue with our lesson. Huh?